Okay, Martin, let's get going and maybe a few more people will join us.
Okay, yeah, this part of it is probably not going to be not that exciting. It's the first half of it, which is just basics of information theory, not much deep learning involved. So I'll just go to the first 1.5 hours of the video, which is just covering the information theory part. Okay, so yeah, so the first thing is why do we want compression? And you know, obviously we know why we want it. Um, you have a bit stream and you want it to be a smaller one, so you know you save bandwidth, you save time, you save space, you know, all sorts of stuff. You save energy, all sorts of stuff. And you know, we use compression every day in our lives, right? So and so there's this very interesting price for compressing human knowledge. So there's a 1 GB file of human knowledge, and then if you can compress it, do a lossless compression to 116 megabytes, then you win €500,000. Um, and yeah, and then the idea is that so why is this important? Like why would there be so much money involved in this? And Peter alludes to it that uh, if we want to achieve compression, we not only have to just do um, we have to understand the actual distribution. We actually have to have human knowledge to predict what's going to happen. So that it isn't just about like classical techniques where we do these uh, which we will get into. The classical techniques is we have distributions and tables of distributions, and then that's it. You know, that's all set. I think that the future is learning those distributions, and then when you learn those distributions, you're actually understand. You have to basically understand the the content, and not just the statistical. Like more than just a shallow statistical understanding of it. You actually have to understand maybe the concepts in the files and how they relate to each other and things like that. To achieve this kind of compression. And so that's where deep learning methods would really come in. Is that then they can get um, a, a more a more deeper understanding of the system of the file and the knowledge, and then can see patterns that isn't easily visible. And yeah, and then there's also the image version of it. I don't think there's any price, but yeah, there's always a competition, a challenge open for the image size. There's a huge block of wall of text here, but I think the point is, I don't know. Can you see my mouse? Um,
Yes,
Yes,
Moshe.
yes.
okay, great. Yeah, there is a decoder, encoder, decoder for images in TensorFlow here, so that they talk about it, and then you know, and then this the challenge is to make to make better images. Um, so I think this is the probably this is like the exciting slide or the exciting overview. Like why are we even talking about compression? You know, what's that seems like you know, some information theory kind of um, stuff that you learn in an information theory class that nobody wants to take in graduate school, right? Um, and so the idea here is that we studied generative models, and then um, so when we do compression, it utilizes the generative model. And so the better the model, the better the compression can be. I think this is sort of a very interesting idea. And I know when we analyzed how good a generative model is, we had bits per dim or things like that. So, but here, if we can give it the source information and the better compression it can do, the smaller it can make it, the more it is the more understand we know that it is understanding what's going on. And so if we have generated models, we can do better compression. If we get better compression, maybe we can get better generated models. So that idea was is interesting, and all of it is fundamental. Comes from the same fact that in order to do better compression, you need a very good probability model, and then generating models. The whole point is for generating models to make very good uh, probability models understanding of the data. And so if it makes a bad one, then it wastes bits by encoding it inefficiently. And so I think the fundamentals of information theory comes in and says, well, how is it actually happening? And so that's the part we'll get into. It's just the basics of it. And then next week we can go into how the deep learning parts are used. Okay, this is a classical information theory based data compression, a PDF, sort of a small booklet. Okay, and then yeah, applications. So all of these, probably used all of these things. Yeah, ZZip and JPEG and all of these things. Okay, and then there was, I think he talks about this TV show. I actually watched this first season of it, and that's when they're doing the compression algorithm. So they develop a compression algorithm that works very well. And I think it starts out being about that algorithm that they want to form a company around. Yeah, and if you've seen, I haven't seen any shows after it, so I don't know what happens later. But the first season I watched, and it was based on it. It was a little bit. I was studying information theory in graduate school, and then the show was like making that feel very exciting, but in reality, there's very little excitement on new compression algorithms and new information theoretic stuff. But yeah, I guess it's all come back around. Like it's sort of a personal, like a strange thing is that when I was working on information theory and all of that is related to cryptography and related to coding theory and all of that, all of it was considered very boring and sort of like not exciting field, right? Especially cryptography. And I remember taking classes on all the algorithms and all of that, and it was like, well, basically felt like all of this stuff was cut and dry, and the basics was it. But then cryptocurrencies happened, and you could see how the fundamentals of those cryptography, created something that was that nobody anticipated, and so maybe the idea of compression is going to be the next thing, or that can really push things along. But yeah, you never know. I mean, when I was learning cryptography, it was just considered boring. Basically everything had been solved, and it was just a domain of all mathematicians who did some algebraic theories, and everything else was cut and dry. But yeah, and cryptocurrency changed all of that, and yeah, and same with compression and things like that. I had the same feeling about it, and especially watching the show, you feel like, well, everything is cut and dry. Why all of this? But yeah, so that's just my personal aspects of it. Okay, so we can move along to some real some real ideas here. Okay, so he talks about universal data compression. So is there an algorithm that does universal data compression? And and the idea is it's no. I mean it's a little bit contrived, this proposition, because when you say compress, it must make it smaller. So um, that's the requirement, that whatever string you give it, it will just make it a little bit smaller. And so you can see that this isn't possible, because if you had something like this, if it could compress every bit stream, so it would always make it smaller, then you could start with a bit string, compress it to a smaller one, then give that B1 back, and then get a smaller B2. And eventually, if you keep doing this, it has to go to 0. And then so that leads to a contradiction, that of course you can't have a 0 bit string that represents information. So so there's a contradiction. So it's just like a proof by contradiction, but the assumption is that the compression always makes it smaller. But it doesn't say about yeah. And but the idea is how much. What if it made it smaller and smaller, and then it stopped? Like that joke. Like if you have zip, then you could. What if you zip the zip again and again and again? We just keep getting smaller and smaller and smaller, right? But of course it doesn't, right? Because it only does it the first time, and after that it starts getting bigger if you like put zip file inside a zip file, because it reaches a limit, and it sometimes grows or sometimes can be the same size. Okay. But the idea is, what is that limit? What how do we know if we can this is the most we've compressed? And it's going back to the challenge, the €500,000 challenge, is, well, is 160 the limit, or is maybe it's 80 megabytes the limit? So how do we get to that? The ideas behind it. Okay, and then there's a second proof, also by contradiction. So suppose there's an algorithm that that you can compress any string into a smaller string. Then you take 1,000. I'm sorry, 1,000-bit strings. Take all of them, and then you make it smaller. So there are 2 to the 1,000 possible bit strings with 1,000 bits. But if you use 999 bits, then you cannot possibly encode all of the bits. So if we take if we take every possible bit, then and if we only have 999 bits to represent it, it's just not possible, because we will lose something. So it's a different way of proving similar ideas. So why compression is possible? So here in this text, if you read through it, you'll see from the second sentence, you can still read it. It says, in a publication of new scientist, you could randomize all of the letters, keeping the first two and the last two the same, and readability would hardly be affected. My analysis did not come to much, because the theory at that time was for shape and sequence recognition. So the first and the last two letters are the correct ones, and then the middle parts are just randomized, and you can still read it. Um, so yeah, I guess we read the first two letters and the last two letters and look at the shape of it, and then have a pretty good idea of what the word is going to be. I think this is the this is the one of the core idea of like coding theory, or is that the if you can just figure out from just the first and the last um, what the word is going to be, and then the context before and after, what what everything is going to be. So in a in this high dimensional space, um, if if you see this word, then you immediately know what the right one is, because in this high dimensional space there are only very few words that are real, and then anything close to it, even with errors, you can immediately see, oh, that's the right one, that's what they meant to send. So there is that space between it, and then we when we read this, there's a lot of extra data that is being presented to us, and we don't have to process it, or our brain has already figured out how not to process it. Um, but we just have enough of a buffer um, between the actual correct things, and then there's a lot of things that are around it that are error prone, and we just can process it. We can deal with that error. So the same idea is that, well, if there is that kind of space in the error, we can, the computer can squish it all out into smaller data and then expand it to the right answer later on. Okay. Okay, and then we have that was for text, and here's images. And if you create a noise, white noise, or this kind of noisy image, it's just not compressible at all. But if you have actual real images, it's compressible, and that's because there one pixel has a very good correlation to what is to the next one. So if since the flower, if it's yellow here, then there's a high probability there's a lot of yellow around it until you reach an edge, but then you can encode the edge with some extra bits, and then the other ones are now more green. So that there's a lot of regularity in our data. But if we look at this one, it has a lot of noise and you can't compress it. Okay, so that was just just the basics of compression. Why it would be could be exciting, or um, what the background is. Okay, so I think we'll go through these three things, and these four things, and then the deep learning parts are next time, and how they relate to it. But these are mostly information theory kind of discussions. So okay, so let's first start with the coding techniques. I think it's coding of symbols. How do we code symbols? And and then you've probably seen this. How do you encode ASCII? You get 7 bits per character, and then you have 128 of them. I think it's if you press a key on the keyboard, on the keyboard it sends the 7 bits across, or 7 bits across to tell you which key you pressed. So that's the simple way of doing it. I mean, so so when you make keyboards, or when you make these interfaces, then you don't have to worry about it. You just get 7 bits, and then that tells you which key was pressed, and you can figure out. Okay. So here in the previous one we had 7 bits. So you could take 7 bits and okay, this was the symbol, and then you take the next 7 bits, and then what was being sent. But what if we change it to variable lengths? So instead of always being 7 bits, it could be 1 bit, and the next letter could be 2 bits, and then the one could be 10 bits. It's just a number of variable lengths. So then we have this problem of how do we avoid ambiguity? So if I get a stream of bits, then how do I know where one starts and where the other one ends? And the solution is simple, right? So the solution is ensure that no code word is a prefix of another. So if A is 0, then B cannot be 0, 1, right? So you can't have one word um, A be a prefix of another one. So if A is 0, then B has to start with 1. And then if then C would have to be, couldn't just start with, there'd be confusion. Okay, do you mean B, or if we said 1? So then there would be 1, 1, and then, or 1, 0, and 1, 1. So there would always be this uh, way of encoding so that you know when you've, so that there's no ambiguity, that as soon as you get a bit, you know if this is the end of the symbol or if it's not the end of the symbol. Um, okay, and so there's two approaches, I guess. Um, okay, so this part I sort of jumped the gun a little bit. Okay, there's two ways of doing it. So I told about the second part, the prefix code, and the other way is just to say, well, just put a stop character between each code word. So you'd say, okay, you send one bit, then you say, there's one bit, and then you wait a little bit, or you send another symbol for the, yeah, depending on the communication, you can wait. Or if it's on the disk, and you have a special symbol for stop or something like that. And so, yeah. Um, but and then the second part is the prefix code, and I think this is the Morse code part. So Morse code is, yeah, if you listen to Morse code, it's a short beep. So let's look at A. Then it's a beep, and then it's beep for a longer one, and then you have to wait a little bit, and then it starts again. Right. So like the classic example is the SOS, right? So it says beep beep beep, and then you wait a little bit, and then you do long beep 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 beep, and then you wait a little bit, and then you say beep beep beep, and then you wait a little bit, and then you say, if you want to repeat this, beep beep beep, and then you say beep beep beep. I think it's supposed to be 3 times as long, and then you wait for like 2 times. Yeah, the advantage is like people can, if they could get really good, then they can send messages very fast, and they can make the beeps really really fast. Yeah, but this is one technique where you use a medium gap, so you have to wait a little bit between the letters to know um, to know which the next letter is. And as you can see, they did they set the beeps and the short and the long beeps, how long they are, depending on the frequency. I think it was some book they went through and then made a distribution of all the letters that were used in the book. And so E was the most used one. So then, it's just a beep. And then I think the next one was A or I, maybe I, and then 2 small beeps. And then I guess T, and then an A. And so it goes up the beeps. And so I think here he makes a very apt comparison, is that the more points you get in Scrabble, the longer the beeps and the dots and dashes, or the beeps you have to encode it as, except for the numbers. I guess the numbers are. But that's the central idea, is that the the more frequent it is, the more points in Scrabble you, the more frequent it is, the less points you get in Scrabble, the shorter you can encode it as. And as the opposite, you get, something like a very unusual one. I guess the longest one is J. So you get a lot of points in Scrabble for it, but then you also have to expend a lot of bits. So J, Q, Y, I guess Y, surprisingly Y. Yeah. Okay. Um, Okay, and so the next one is the prefix codes. And the prefix code, as I said, is that you the one symbol is not the prefix of another symbol. And so they just call them prefix free codes. And the data structure used is called binary tries. And I think it's also pronounced trees. And tries and trees. Yeah. Yep. And then we have okay. Yeah, I wanted to tell sort of a C++ joke here on the binary tries. Well, that's from a podcast, C++ podcast. I don't know if you're a C++ programmer, but basically, there's a podcast by a guy who invented this library called Catch, which is used in C++ testing. And his next project was a library for binary tries. And he was adamant about calling it tries instead of, or maybe he called it trees, because if then he didn't want to be known as the catch, the try and the catch guy, right? In C++ you have try catch, and then he has the two libraries called catch and try. So he called them trees, I believe, so that he wouldn't be called a. So anyway, that's my C++ joke. But okay, so getting back to it, in binary the tries, what happens is that the leaves um, leaves are stored with a symbol. So leaves are the ones that don't have any children. So this is just a binary tree. So there's a left and a right, or a 0 and 1. If you don't have any children, I guess you're represented by null. If you've done any of those interview questions, you have to deal with all of these. So it's just a binary tree. And then if you have no children, then you have your leaf, and then a symbol is encoded in the leaf. And so here, if 0 came in, then you immediately know it's A. E came in, then it's 1, 1, 1, 1, and then you know it's B. It can't be anything else because nothing is a prefix code. So C is 1, 1, 0, and that can't be prefix of anything, right? So that this idea of being prefix free means that that you can only put symbols in a leaf. And then if that's the case, then it becomes prefix free. Because once you end up in a node, obviously you can't go anywhere, so it cannot be a prefix one. So if C had another child node, then C would be a prefix of some other. So yeah, so that's the basic idea, right? So and so the question is this unique? And turns out it's not. So here's the same representation. You can also encode it in both. So I mean, it's kind of easy to think about, right? So you can make what is this, 1, 2, 3, 4 level binary trees. You have 5 symbols, and you just put 5, and then you prune all the ones. As soon as you put a symbol, you have to prune everything, and so you can create all sorts of trees, right? So it's not a unique way of so prefix free code is not unique. So that's the point. Okay, and so then the question becomes, if there are multiple prefix free codes, is there an optimal one? Yeah. So is there an optimal one, and under what condition are we optimizing? Is the length of the the bit string. So in this case, this tree took 30 bits, and then this bit string took 29 bits. So if we look at all of the bit strings, all of the binary tries, all of them, can we find the one with the smallest bit string? And so that would be our optimal prefix-free code, right? And so obviously one way of doing it is just like make an algorithm that goes through every single one and then just say, okay, this one took this many bits, this one took this many bits, and then, but there's this faster way of doing it called Huffman codes that builds an optimal prefix-free code. So here's the algorithm, the Huffman algorithm. So I think I will go with the basic idea, and then I can just show. He did this on um, the slide, but I'll just do the other one, and then I can go back and forth this one, right? So the first stage of it, I don't have a pen to like the digital pen or whatever to do this. So the first step here is so every symbol has to have a probability pi. So here we have character, and then we have the frequency. So if we divide by the total, then that would be the probability. But here we're using the frequency as a proxy to the probability. And then so for each, we start with one node corresponding to each symbol I. So let's just consider all of these symbols and just put circles around them, and they're like free floating nodes right now, right? So that's the first step. And then this is the while loop part, or repeat. Select 2 tries with min probabilities, and then merge into a single try. So the first step we do is we find 2 of the smallest ones. So we'll go through this one, and then we say, well, there's 3 of them, C, D, and exclamation marks. They have the lowest frequency, and so the lowest probability. So here we in this one we took C and the exclamation point, and then we combine them into a single. These are the trivial tries where we just have the single nodes, and so we combine them together by making a node without a symbol. Right? So, and then what happens is this node here, I can't write on it, but we can imagine it's 2 now. This value here is 2. So we have the combination of C and exclamation is 2, and we've created this. So now this layer we have these four tries. D, the try for C and exclamation mark, R and B, right? So we have these, and so then we again do the while loop and say we find the 2 lowest ones, and the lowest ones are D is obviously the lowest one, 1, but then we have 2, B, R, and then this try, all of them are 2. So we have D, which is 1, and then we have all of these are 2. So here we selected this older try to be to be joined into this new one. So then it becomes 3. So once this becomes 3, then the lowest ones are R and B, which have 2 on them, right? And so then we join them, and then they become 4. So we have 2 tries, one is 3 and one is 4. So 3 and 4. So it's still the 2 lowest, and then we join them, and then it becomes 7, and A is 5. And so we join them together, and then we've created a Huffman code. And and this is just the algorithm for doing that. We don't know if it's optimal or not, but there's we'll do a proof of it that this is going to be optimal. And I don't know what this is. It doesn't work. It wasn't shown in the. Oh, did it work? Okay, I guess I'll play it if it works. I don't know how. Anyway, I don't know. Maybe it's broken. Yeah, the Huffman code is used in all of these technologies. Okay, so that's just the coding of symbols. How do you make make codes out of them? So we'll just do after this. Then we'll do some theoretical limits from all of these. Any questions, or should I move along?
No, keep going.
Okay, great. Okay, and then so we've probably seen this hundreds of times. The entropy, the definition of entropy, it's the summation probability log 2 of one of the probability. Sometimes you also write as the negative in front and then the p on the top because of the property of log. So that's called entropy. And so you can calculate the entropy if you have a distribution. You just put all these values in there. All this is in log 2, and then so you get these numbers. And as you can see, if the probability of something is very large, like here it's 0.75. So 3 out of 4 times you get this. So the entropy is lower because you know most of the time you just get this single number. So there's not that much information being conveyed here. But here they're all kind of equally likely. Well, the first 3 being slightly more, or at least double more. So there's more information. There's more. You can't just assume, yeah, it's probably going to be this. It could be, a lot more varied. So it does that's why it has a higher entropy. So if it was completely flat, it was completely random, then it would have the highest entropy. If all of it was in one place, then it would have the lowest entropy, right? The zero entropy, because you always know what's going to happen. Okay, and then the entropy coding. So here that's another similar to Huffman coding. You set the code length to be 1 over the probability, and you can get something like this. So A would just be 0, and then you could just put B and C and D here with these different probabilities. So the lower the probability, the more bits you'd get. It's similar to Huffman coding, right? You'd have this. You'd have the same thing. So C and D would be first together, and then they would be joined with B, and then they would be joined with A. But here we have the probability is dictated by the code length, the upper bound of the code length. So here, so we have half, and so 1 over half would be 2. Log 2 of 2 is 1. So we know A is can just be set with 0. And then if we look at B, it's 1/4. So this would be log 2 of 4, which is 2. So we do need 2 bits for it. And then 8 would be 3 bits. Yeah, 2 to the 3. So 1, 2, 3, 3 bits. So it's either 110 or 111. So yeah, just the and you can see, you know, it works out here. I mean, it works out well because these are powers of 2. But that's the idea. Okay. So we first start with this Kraft-Macmillan inequality. Okay, so we have to decode this. There's a sorry, there's a whole bunch of stuff here. So part 1. So if we have a code for any uniquely decodable code, so just a code that works, I guess that's what uniquely decodable code is. If it's not uniquely decodable code, then it probably is. Yeah, it's more work, I guess. But just the codes that we're discussing, what we have is so let's decode this symbol. So S is the symbol, and W is the code word. So if the symbol is A, then the code word would be like this, like 0 or 01 or something like that. And C here is the code that goes here. So these are the symbols. And then L is the length of the word, code word. So L here is used here. So here the idea is if you take the length of it and then you take the 2's power of it and you sum over all of the lengths, it must be less than or equal to 1. And which makes sense because yeah, otherwise, you know, if this wasn't the case, then it would be prefix of something else. So so the length of it will, you know, the more rarer it is, you have to give it 1 extra bit to decode. So that's part 1 of it. So you can take the lengths of all of them, take 2 to the power, and then you sum it all up. It's be less than or equal to 1. And so that's a requirement for a uniquely decodable code. Right. So okay, and so there's a part 2 of it that says, so if we have a set of lengths, so L is a set of L lengths, and if the summation of all of the 2's power of negative L, if it's less than or equal to 1, then we can create a prefix code such that if we have L words and we give L, you know, each one word length Li, then we can create a prefix code out of it. So it goes both ways. So if you have a prefix code, then the powers of the length, code length, has to be less than 1. If we have such a, you know, set of code word lengths, and we sum it all up, it has to be less than. Then we can create a prefix code from it. Okay, so here then we'll look at the sketch of the proofs on and yeah. So just a quick. So this was the first part, right? When we said the summation of the code lengths, the 2 to the power of 1 code length should be less than or equal to 1. Okay, and so here's first assumption is let's say we have n symbols and n code words, and then the length of each of them are L1 to Ln, and then we'll order them from smallest to largest. And then from this one, we can create a tree or a trie, but we can create this. So usually this would be the symbol, and this would not have any children, right? The red ones are the where the symbols are, and so there would be nothing underneath it. So for this proof, what we'll do is we'll take this and then just fill it out until it's a full tree. So every one has a children on a certain height, so until depth 4. Okay, and so what this shows is that for every symbol, there is 2 to the ln, which is the longest, minus li, this length. So here ln would be 1, 2, 3, and then li would be 1, 2. And so there's at least 2 to the 1 leaves covered. Yeah, and so since from by definition we cannot, these two symbols cannot have the same nodes underneath it. So each of them have their own. So if we sum it all up, if we sum up all of these nodes underneath these, then it should be less than the total number of nodes because there's no double overlap, right? So this one has these nodes. This red, these ones have these nodes. So there's never an overlap. So if we sum it all up, all of these underneath it, it must be less than or equal to 2 to the L over n. And so and that just implies if you divide, if you just divide it, then that 2 to the minus li must be less than or equal to 1. Like a simple proof of how this works. Okay, so we can do the part 2 also. So then we have a sequence of lengths, Li, such that the sum to the minus Li is less than or equal to 1, and then we rearrange them in order. And then we start with a full tree of depth, highest depth, Ln. So the depth is the number of, so the highest here is 4. And so for each I, we can pick any node Li of certain depth that is available. So you pick this one, then the rest doesn't, we pick the first one, you could also pick this one, then the rest would be unavailable. And then the question is, well, is there enough space? Will there be, is it possible that you have one of them you couldn't fit anything in, but since it's all less than or equal to 1, 2 to the Li is less than or equal to 1, it is possible. So this probably needs a little bit more explanation, but yeah, we can just leave it as is that it is possible to put all of these. Obviously, non-unique ways. You could, instead of putting it here, you could put it up here. This red value, you could put it up here, and then you'd get shift around. And obviously, this would then have to be put over here. And then, well, if you put this one here and then you put these two here, then there's no way you can put it, right? So that code wouldn't work. And so you'd have to restart again and say, well, okay. But if we do it by the length, so you only have 2 choices. You go left or right. And then the second one, you go 1 level down. And then you go 1 level down. And then with this argument that they say is that, yeah, there should be enough room for it. And so that's the proof of it. And so the consequence of this, the big result here is Shannon's theorem. I don't know if it's called Shannon's theorem. I think there's other Shannon's theorem, but the idea here, main idea here is that so LA of C is a new symbol. So it just stands for the average length of the code. So as you can see, this is the definition. Um, so the probability of xi times Li. So that's the average length. This average length of the of all the codes in the message is bounded below by the entropy. So you can never ever have an average code length that's less than the entropy of the distribution. And so here's a proof of it. Let's I think using the first two inequalities. So here's h of x, and this is the definition p of xi log of p of 1 over p of xi, right? That's the definition of it. And we have average code length, which is the probability times the code length, right? So that's pretty straightforward. Just giving the definitions, and then we factor pxi out. So then we have because both of them have pxi, so we have log 1 of pxi minus li, and then the next step is L of, we want log 2 in both cases. So L of I is the same as log 2 of 2 to the Li, right? So this is just taking the log and taking the exponent. And so because of the properties of logs, we can put these together. So so here there's one more step missing, is that if we put, since this is negative, this will go to the bottom. So this would be p of xi times 2 to the Li, and then the 2 to the Li is flipped to the top by making it 2 to the negative Li. Right, okay, and then, so this step is the one that's a little bit tricky. This is using this inequality. This might look, the Jensen's inequality says f of x is less than or equal to, f of expectation of x is less than or equal to the expectation of the f of x, right? And given that f is convex, but this is flipped the other way, and because log is concave, so it flips out the other way. And if you don't want to look at it that way, you can just also look at it this quantity right here. As you can see, this is very close to the KL divergence, right? So if you flip p of xi and then you put this 2 of negative Li down, then it becomes a KL divergence. And KL divergence is always positive, right? So that says this must be, when you flip it, it becomes a negative here. And so then we can say, well, since this part is KL divergence, negative of KL divergence, it's always less than or equal to 0. Or you can use the Jensen inequality to bring the log out. So when the log comes out, you have p of x and p of x canceling each other out, and then we just have sum of 2 to the negative Li. And this inequality, the sum over here is less than or equal to 1 from the previous inequality that we talked about, the Kraft-Macmillan one, and so the log 2 of 1 is 0. So this basically says that the average length is bounded below by the entropy. So you could never have a code that's where the average length of a code word is less than the entropy of the distribution. Okay, and then so there's a yeah. So so we're doing the converse of it. So the question is, can we have a prefix code with lengths li? So if we did the length of each code is log 2 p of xi. So we know the probability p of xi, right? So let's say we'll assign li the length of the code 1 over p of xi. Is it possible to have a code that way? And so we can again use the same idea. So um, 2 to the negative li from the Kraft-Macmillan inequality, right? So if this is less than or equal to 1, then we know that we can create a prefix code. Right? That was the second part of the Macmillan inequality. So we start with li, we substitute this in. So this is log 2 of 1 over p of xi. This is less than or equal to it because this is the ceiling operator. So we remove the ceiling. So then because this is the negative, of the 2 to the negative, so it's in the denominator, so it becomes less than or equal to, and then so here the 2 and the log 2 cancel, so it's just p of xi, and then this sums up to 1. So this is less than or equal to 1, so then it is possible to create a code word with this scheme that we take the log 2 of 1 over the probability, then we know, okay, so we can create a code word that way. Yep, so so there's a code with these lengths. Okay, and so so if we create a code word like this, what is the expected code length of this code? What is the code length? And so it's just, that's LA of L subscript A of the code, which is the the average, which is the probability times the length of the code words itself. And then Li is substituted from up here, the log 2 of 1 over p of xi. So it's the probability of that of that of that code of that symbol times log of 1 over p of xi, which was the length of the code that we described up here. And that's Li over here, is the length of the code. And then, you know, oh yeah, oh, okay. And then, so this one is that the ceiling must be less than 1 plus the value, right? Because the ceiling is just rounding up. And so it must be within 1. And we can take the 1 out, um, and then this part becomes the entropy. So it's 1 plus h of x. So it says that if we use this method, then the average, or the expected, or the average code length is less than 1 of 1 plus the entropy. So we have an upper bound. If we use this technique, we have an upper bound on the size of the code, the average size of the code. Okay, so I know it's a lot of proofs, but yeah, but I know Peter said this is one of the most interesting, or elegant use of mathematics here. So I think that's why going through this. But yeah, so let's prove. Let's do another proof here, and then that's what we alluded to. That Huffman codes are optimal prefix codes, and if you remember the Huffman codes where we took the lowest ones, we turned them into a tree, and then we took the next one, then in a tree. So here's a proof of it. It's probably more technical than insightful, but the proof is by induction. And so if you're familiar with it, induction is basically you start with a base case saying, you know, let's start with the number of symbols is 1. And then if you just have a single symbol, then if you make a code, then it's it's just a single symbol. So it's obviously going to be just 0 will denote what. It will just be a single bit to denote it. Induction. So for n equals 1, it works because there's only one representation. You either say 1, 0, or 1, and it's always 1 bit. So there's no other. So then we say, okay, when n equals 1, we know it's true because it's very simple and we just checked it. Let's assume that it works for some number n minus 1. So Huffman codes of size n minus 1 are optimal. So let's start with that assumption. And then the step is to say, well, if that n minus 1 is optimal, then the n Huffman codes of n are also optimal. And that's the argument here. So, and then as you remember, we first start with the lowest probability symbols, x and y, right? So you have x and y and you start with those. And the observation is that optimal prefix code always have 2 leaves in the lowest level branch. And so if we go back to this here, basically saying that at the bottom there's always 2 at the bottom of the tree, the ones with the lowest probabilities always are connected this way, that they're left and right with a shared parent. Right. And well, why does it have to be? If that was not the case, if this was not here, then and this was the lowest probability one, then like why would you waste this space? You just move this up 1 space and then you'd save a bit, so you didn't have to come down here. Right. So then that would so we can assume from the way we constructed it is that if we take if we construct a Huffman code, that it's the lowest 2 ones are always going to have always going to share a parent node, right? So that's the second part of it. So they will always have the 2 leaves in the lowest branch. Otherwise, you don't have that. You don't. And so without loss of generality, let's assume they have the same parent, because if they if we have multiple if you have 3 of them with the lowest probabilities, then you could have different parents. But let's just assume that x and y have the same parent. Otherwise, we could just choose the other 2. So, but then you don't generality by saying like, well, x and y must have the same parent, because if not, then you can choose the other one, and it's the same process. And so here's the argument that they make, is that, well, because of what we discussed, x and y must be 2 leaves at the bottom of the tree. So the cost of having both x and y, is always px plus py. So if we removed yeah, so it is always the same. No matter what we do, the lowest ones, px and py, are always there. And then if we remove x or y, then we know that the constructed of n minus 1 is is already optimal. That's the induction assumption, is that we, if we constructed a Huffman code, then it is it is already optimal. I know this isn't there's some steps missing here, because normally you would say, well, how do you know that if if you can't just take the lowest one out, and then you might -1 might have um, um, a slightly different structure. So all of that needs to be taken care of. But this is a general idea, I think, and you could get through it with the same argument. So it wouldn't be it's not 100% rigorous, but its basic idea is that if you have a tree with n-1 elements, it's optimal. Then if we add one, the lowest one, it always has to be at the bottom. So there's no other choice. So there's not much. So it's always going to be optimal no matter what. You always have the same cost of adding that smallest value. So that's the basic idea. But there's a little bit more argument that you could make for like a fully rigorous proof. But that's the main idea of it. Okay, so let's do a quick recap of it. There was like a whole bunch of theorems here. So um, so we did the entropy, which was the p of xi log 1 of pxi, and that resulted in the Shannon's theorem that says that if a data source p of x is an order 0 Markov model, then any compression scheme must use greater than or equal to the entropy bits per symbol on average. Right, so that this was the idea, was that the entropy was the lower bound on the average code length. And so on the lecture, he makes a more on this. It's a 0 Markov model. What this means is that we assume that each symbol is independent of the symbol before it. So if this was a text, then we would assume like every letter was completely independent. We just have the probability of how it occurs in the text, but they're completely independent. But that's not the right assumption, right? So because if you take all the letters and you move them all around, then it's invalid text, right? Obviously, there is a lot of order to how the words are arranged, or how the letters are arranged. But in the case of zero order Markov model, then the entropy just basically says, yeah, you can't go lower than that. And the Huffman one, the second theorem we proved, if the data source px is of order 0 Markov model again, then it uses, there's an upper bound, h of x plus 1. So the code word is bounded below by h of x and above by h of x plus 1. And if the probabilities are exactly, to the powers of 2, like 1/2, 1/4, 1/8, 1/8, then it exactly matches the entropy. Otherwise, there's an average 1 extra bit to all of it. Okay, so that was the theoretical limits of the main idea is like the Shannon the entropy. Shannon theorem says the entropy is the lower bound of the average code length, and then Huffman says, well, if we use the certain scheme, entropy plus 1 is the upper limit of it. Right. So any questions on that? Okay. Oh, okay. Hopefully that wasn't too super boring, but it was just going through a bunch of proofs. But okay, let's go into coding considerations. So what we here we're assuming that our probability p is always correct. That we get the text and then we get the probability of it, or we get the count of it, then we do the encoding. but then, in that case, then you also have to save the encoding into the file, and then you have to transmit. But sometimes you just, you just start with an assumption. You already start with a probability distribution. What do you do in that case? What happens if it's not correct, right? So if you calculated the probabilities on one text, one book, and then but you have to compress another book, but then you don't get to analyze the probabilities, um, then what happens? And so okay, and so there's a derivation which is so I'll go through it. It gets us this concept of KL divergence very neatly here. That's one of the interesting things here. Um, so LA is the average code length again, which is the sum of the probability of the code word I times um, the code word length, which we said is going to be log of 1 over pi. So it should be the upper bound, but we'll just assume that it doesn't have to be binary, or it just matches perfectly. And so here we do the add and subtract, the same thing trick. So we add pi log of 1 over pi and pi 1 over log of pi. The entropy, we add the entropy and subtract it. So it's the same as the one before. And then as we see down here, the second part is the entropy, and then this pi can go on the top here because we're doing a negative here, and then this is log. And from the definitions, we can see this is the second part is the entropy of P, and this here is the KL divergence. So what this says is that if we choose the wrong distribution, the price we pay is the KL divergence. And this quantity is called the KL divergence. And yeah, and then here's a small proof of that the KL divergence must be greater than or equal to 0. And again, he uses here you could Jensen's inequality, because this is we have KL divergence of P, distribution of P again with compared to Q, and that's Pi over log Pi over Qi. That's the definition of it, from up there. And yeah, and this is just flipping the Pi and the Qi. You can bring a -1 up here, and that's how logs work, right? So you're taking the -1 of it, and then the -1 can come forward in the multiplication is the power inside the log. And so you use the Jensen-Shannon inequality again. And then since log is concave, so it works the other way. And so the log comes over, and then everything is inside the brackets. So expectation of log of x is greater than or equal to the log of the expectation of x, right? So that's what's going on. The p and p cancel, and the sum over qi is 1, and log of 1 is 0. So the KL divergence is always 1. So you always pay a positive price. So if your distribution doesn't match, your code length will increase. So that's the cost of not getting the wrong probability. And if they're equal, this should be 0. So if P is equal to Q, then yeah, this would be log 1, and then this would be 0, right? So if Pi is equal to Qi. Okay. So that's how the KL divergence comes in, and what of approximation. Okay, so then the question becomes, what if P of x has high entropy? What can we do? How can we decrease entropy? So high entropy means longer code word lengths. So one of the things we can do is decrease the entropy by considering a conditional probability. So instead of entropy based just on X, we condition on C. So here in this case would be like, so instead of just the probabilities of like how all the letters in the whole book, we say, okay, what is the probability given that the letter that came before it was this? So if it was T, then what, um, um, or if the word was N, then you say, okay, what is the probability that the next letter is T? So it would have a different distribution than if the previous letter was C or something, right? So, um, or XT or something like that, so the probabilities would be different. So you can add a conditional probability to it, and then maybe you'll get these probabilities will be more, there'll be less entropy. And here's, I think this is a proof saying the conditional entropy is smaller, but I don't think this is correct. Um, um, because x of c is less than or equal to the entropy, which he says is equal to p of x, but this would also, yeah. So if p of x is not conditional, then this would also be p of x, and then p of c would all sum up to 1, and this would be, but I don't know how this implies inequality. But anyway, but the point here is that, well, autoregressive model already does this, right? So that was the first model we looked at, is that what's the next pixel going to be provided I look at every pixel that I've already generated. So this is the job of the autoregressive model. So we've already done this. So um, we can already create probabilities this way. And we know from this that the conditional is always going to be less than the unconditional one. So we can never be worse off by adding more history to it. But I don't know how this proof works, but yeah, don't think this is correct, or I'm misunderstanding it. But we can just think of it like the conditional is always lower than the conditional entropy is always lower than the entropy. Okay, and so yeah, this plus one thing, like we might say, well, like we have Huffman codes. It adds 1 bit, so why are we worried? It's not, it's upper bounded by 1 plus the entropy. Why aren't we just happy? Like we got, we have what we want. But it could still be bad. And so he shows an example where if we have good predictive models, and so it's very good at predicting the first letter. The entropy is 0.569, but the best per symbol code is bounded above by 1.56, and in practical it is 1.1. So it is double the value. So it can be high cost, if in certain conditions. So um, okay, yeah, it can be high cost. So um, and I think the maybe the good example of here is that of a fax, right? So if or um, so the idea of the fax is it's black and white, so it only has 0 and 1, black or white, and then most of the paper is white. We only have some parts that are black, right? So most of the time, the data is, it says, you don't print that pixel, but then in certain cases there is, there's a black dot, and so in that case, we will end up spending a lot of bits in coding encoding the black and white. So 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 this +1 might be, you know, very bad, especially if we're using, you know, a telephone, and then we have to send the code and over a telephone. Uh, but yeah, if you've used faxes and the slow transmissions and all of that, so they created something called run length encoding. Um, so a document can have up to 1728 pixels per line, and usually it's most of those are white. And you know, when you print a document, it's just like coverage is like 10% is black, or 10% is actually you have to put ink on it, right? So so the technique they use is called run length encoding. So they encode the symbols are 3 whites or 1 black, or 2 whites, 2 black, 194 white. So they have a encoding for the run. I don't know what they mean by 2 Huffman codes, because I mean, I don't know why you just use the same one, single one. But yeah, but obviously it can't be a prefix of the other one, right? So um, so yeah, a black dot is the highest probability, and then you have spaces of 3 whites, and so these kind of and they've analyzed the probabilities of it. So there's a lot of these 64 lines of white, and you know, all lines of white. So all of these are encoded in the Huffman code to send fax. So that's how they developed the fax, and so that it was efficient to transmit along phone lines. Um, and this was the now this was another idea of how much information is there in the English language, um, and instead of just doing the um, probabilities of each letter in the whole message, Shannon did this where he asked subjects to predict the next character. So if you know, as you can predict the next character as you go along, and then if you're right, he will tell you, yes, you're right. Otherwise, you have to try again and again until you get the right answer. It's like a hangman, but you know, you're just putting in the last letter. So 80% of the time you could get it in the first guess, and then 8%, 3%, 2%. So most of the time, you know, you immediately know what the next letter is going to be. So there's only a few times when something new happens. So most of the time you really like can know what's going on. 20% of the time is something new. You can't tell what's going on. So Shannon's estimate was about 1 bit per character. So you could compress um, um, just from of English, it only takes about 1 bit per character. And so if you look at the challenge, the 1 gigabyte challenge, right? And I assume that one character is stored as seven bits or 8 bits. So if really you could encode it as 1 bit per character, you could create a good enough model that you could encode it as 1 bit per character, then it should be 1/8 of the size, and 1/8 of 1000 would be like 100 something, 160, around that, 160 or 1/7 of it. So maybe that's, yeah, that's sort of, this is the empirical thing. That's the in our heads what we have, uh, the actual entropy of English language in our heads. And if we have a model good enough, then maybe we can reach that 160 megabytes mark from the 1 gigabyte file mark. Okay, and then this is just the entropy that we've reached so far. This is the 7 bits per character, so we don't do any compression on it, right? So we just store the characters, and then I think this is this is the actual entropy. If we just calculate the distribution of all the letters in the English language, and then and calculate the entropy. Huffman coding is obviously going to be a little bit worse than that, right? Because the lower bound, so it's a little bit more. And entropy, groups of 8. So instead of using one letter at a time, you start doing 8 letters at a time. So I mean, of course, your dictionary becomes like huge. So instead of just having 128, you have 128 to the power 8. So that's a lot of probabilities you have to take care of. But then it, you know, the bits per character goes to 2.4. And then I guess if you keep adding more, it asymptotically approaches 1.3. And these are some programs. I think I know compress is, I don't know what this is. Zip is the Linux zip program, and these must be other two algorithms or software to zip it. And so this is just a basic idea of it. So there's still, even if you took the state of the art bits per character, and then yeah, you would the 1 gigabyte would probably still just compress down to 250 or 250 or if it's 8 or 250 or 300 megabytes. So there's still some gap from one bit. So even if you use the standard compression. Okay, so this is the coding considerations, and then I think I can go through. This is these are the. I think I'll just go over this part. That's not deep learning related. In the video, he took a break around here, but I think we still have a little bit more time to. Any questions, or should I move on? Okay.
Keep going.
Okay, great. So we can go to this idea of arithmetic coding. What is this here? So this +1 was the overhead +1. I mean, Shannon's entropy was the lower bound. We know like we can't do better than that. But this +1 was because of Huffman coding, because we had a special algorithm, and this +1 came from an algorithm. Like, can we do better? Can we just get rid, can we get rid of this +1? Can we do better than this? Okay, and so all of these, and one of the things we talked about is that we can, put symbols in a group. We can say, large and larger. So instead of just letters, we can say two letters at a time, or 3 letters at a time, 4, and things like that. Yeah, and so we, but with arithmetic coding, it's a completely new way of encoding, so that we don't have to worry about this. So let's just get into that and how to do it. So let's assume that the distribution here is probability of A is 0.8, probability of B is 0.2, and then let's figure out how we can encode this word ABBA. So what arithmetic coding does is, so your first interval is between 0 and 1. And then since A is 0.8 and B is 0.2, you divide it into two subintervals. So 0 to 0.8 is A, and 0.8 to 1 is B. So since the first letter came out to be A, then we'll say, okay, we're now in this interval from 0 to 0.8. So we'll discard this part and we'll throw it away. Okay, and then we do the same thing to this interval. We multiply it by 0.8 and divide it into 80% and 20%. So it's 0 to 0.64 and 0.64 to 8, right? So we have two different distinctions. And then we got the next one is still 8. So then we'll still take the green, and then we'll throw the blue one away. Okay, and then we do the same process again. We take 80% green, 20% blue. And now we got the letter B. So we throw the green one away, and then we go into blue. And then we do the same thing, 80% green and 20% blue, for 80% for the probability of A and probability of B 0.2%, right? And so the last one is A. And so we choose this interval, 0.512 to 0.144. And so this basically encodes this interval between 0.512 to 0.6144 encodes the word ABBA. So we'll send the interval, this interval, as our code word. But like, what does it mean to be what does it send an encode interval, right? So that's the obvious question that comes up. So one way naive attempt is, let's look at the interval and find the interval that has the fewest bits in binary fractional. So it's going to be some like 1/4, 1/2, or some to the power of the bottom denominator is going to be power of 4, right? But the problem that comes is like it doesn't work because it can't be prefix codes. So that violates the first problem, the first principle, that it has to be prefix code. So the attempt here is the result here is that have each binary correspond to interval of all possible completions. Okay, I'm not quite sure what this was, but yeah. Anyway, so binary. So
I think it's just the interval, the possibility of those probability distributions being subjected to a particular fraction of a from 0 to 1. I think that's what it's saying.
okay,
For example, in the next line, yeah. So from 0 to 0.225. So that's the fraction.
okay, that makes sense. Yeah. So this is a smaller interval, so you give it 3 bits, and it's 0.11, and then it's 2 bits also. And yeah, okay. And then so for interval of size s, one can always find a code word of length minus log 2s plus 1. So it's based on the size s, the size s of the interval. And so from here, it shows that the code length is h entropy of x plus 2, and 1 plus 1 from rounding up, and then plus 1 from the this plus 1. So there, the plus 1 from the rounding up, and then the plus 1 here. And but you might say, oh wait, why is there plus 2? That's worse than we did before. But the thing here is this: the entropy of the whole sequence, not a code word. So we do have to add 2 extra bits to it, but then but we get very close to the entropy of the whole message itself. So if the message is very, very, very long, then this plus 2 is negligible. and we get very close to the entropy of it. Right. So with arithmetic coding, you can get arbitrarily close to the code length. Sorry, close to the entropy, because this is bounded above by the entropy +2, and so if x is a gigabyte file, then obviously +2 bits is not that much. Okay. And there's some other technical challenges. I think if the interval keeps straddling 0.5, so if the 0.5 is in the interval, then in the I guess we can't send the first bit until we're done. So we're stuck. And so the solution here is to split the message into blocks so that we don't have, we're not sitting there encoding gigabytes and gigabytes on. Also the second problem is we assume infinite precision of the doubles, but there's also a solution where all of this can be implemented in integer implementation. You can always, like, after each step, you can always rescale it, right? So, and store the information and rescale it, and you can do it in integers. Okay, and so I think this is where everything, the autoregressive part comes in. Is suppose we've tamped down and we fixed our autoregressive model, and so let's encode ABBA, and so we get the probability of A and probability of B. We get the probabilities of all of the different things that can happen, and then we divide our interval that way, and then we throw away the blue one, and then we ask it again, what is the probability of A and B, given that we got an A last time? So we'll get a different distribution. I mean, right now it still shows 80% and 20%. Maybe it goes up to, and 40%. So at each step, you could have different probabilities depending on the previous probabilities. So the autoregressive model, you could add, because probability of x2 given x1, so these could be different. It doesn't have to be fixed 0.82. So this arithmetic encoding has that extra feature in that at each step, you can subdivide the intervals in completely different ways, and it still works. And then x3 would be based on x2 and x1, and x4 would be based on x3, x2, x1, right? So that it has, and so you can get better compression by being able to predict from all of the things that came before it. And that's what we did exactly in autoregressive models, exactly for images, was that we looked at the history of everything and we tried to get the probability distribution of everything that could come next. And yeah, and so, but and this is yeah, and obviously when we created new images, or when we just sampled something randomly, and then the most likely would have been chosen or something like that. But here we'll use all of that to do compression. The next probability to determine the interval and to do the compression. So yeah, so there. I probably should stop here, but just one comment is that I think it's yeah, so the bits per dim, and the compression ratio would be a very good metric for the autoregressive models, because I know when at least in at my work, when if we get any probabilities from the deep learning model, you could just ignore it, because it's just um, it can get it completely wrong and be very confident that it got it right, or that the probability doesn't mean anything. It just it just comes with it. But I don't think it gets penalized for. So if it's wrong, For most of the cost functions, if it's strong, it's not penalized by the probability. So it's because of that, I think a lot of the probabilities are just sometimes nonsensical. It's either very confident or just not confident, or there's artifacts like that. So if you train it based on probabilities, then there's other problems, I believe. So, but in this case, it has to get all of the probabilities very close. Otherwise, the compression would be affected. So if all of that comes together, then we can get good compression. That means we get better GANs, and then we actually have a better understanding of our data by how much compression we get, and we have a very good metric of if we're doing if we're doing better or not. Um, so all of this kind of sort of ties together in that that if we can use unsupervised learning to actually get the distributions, very accurate distributions, then we have compression, and which implies that we have better models, and then we have all this theory from information theory to understand what's going on and to measure these things. And then we also have all of the unsupervised learning to generate these distributions um, um, to, um, to create these probabilities without, to create these complex probabilities with trying to find patterns and probabilities without being superficial in the distributions. So yeah, and then so we can continue next week with actually how they're used and all of that stuff. So um, do you have any questions or any points to discuss?
No, look forward to next week.
Okay. Yeah, sorry, this was probably a little bit just not deep learning and just information theory, but hopefully it was useful or
But
interesting.
yeah, but it's foundational to, I guess, what we'll do next. Right? So,
Yeah. Okay then. Well, we'll see you next
okay,
week.
great. Thanks, Mojit. Yep.
Thank
See you all
you.
next week.
Thanks, Martin.